Good morning, everyone. Thanks for attending my talk. So today I will be talking about Bravyi-Koenig theorem in hypergraph product code. So this is a drawing work with my collaborators, Hanzheng, Zimu, and Seven. In order to do quantum computation, we do need like a universal gate set. So any like kind of new information, knowledge that we have about like the family of quantum codes with regards to what logical gates it can perform will be useful in this regard. So, but currently, most of this understanding of like restrictions on the limitations on the logical gates that quantum codes can perform, like most of this comes from results which are like which only mainly for geometrically local or topological codes, and this is using the Bravyi-Koenig theorem. So our goal here is to generalize Bravyi-Koenig theorem to other families of quantum codes, in particular, like those codes that are like not necessarily geometrically local. So in this work, basically we generalize this Bravyi-Koenig theorem, and then we prove a series of no-go results for fault-tolerant logical gates on hypergraph product codes. Which are not geometrically local, but and has like better code parameters. So these results also suggest that you can possibly think about if you have some understanding about the structure of other families of quantum codes, then it is also likely that one might be able to show like similar kinds of no-go results to potentially other families of quantum codes. So one well-known example of hypergraph protocol is the toric code, and in 3D you can perform CCZ gates. And then color code, we can also unfold it into copies of toric code. So no-go result on toric code also imply a no-go. Sorry, go back. Also imply a no-go result on color code. And previously, people have found a lot of Clifford gates on 2D hypergraph product codes, and we are going to show here that there's actually a no-go result, that is that you can't find non-Clifford gates for 2D hypergraph product codes. So these hypergraph product codes are also examples in expanded codes. So these are like a pretty interesting family and has good and is well studied and has pretty good applications. So because like hypergraph product codes are not geometrically local codes, we actually cannot use the usual technique of like dividing these codes into like correctable regions. So first, we need to like generalize the Bravyi-Koenig theorem to all kinds of codes, and then next we have to rely on the structure of stabilizers and logical representatives of these hypergraph product codes in order to put the limitations on the logical gates. So to do the first step, in Bravyi-Koenig theorem, basically it's like we want to put limitations on gates, and the gates fall in this like Clifford hierarchy. So P1 is the poly group, and P2 is the Clifford group. Then the higher level gates in this hierarchy are defined recursively. So for example, Pn will be defined as the set of gates where the group commutation between Pn and P and P1 is in Pn minus 1. So this is the like well-known result of the Bravyi-Koenig theorem for geometrically local codes. So what it says is that if you have a unitary operator implementing a logical gate on a code that is geometrically local, and this code is embedded in like a d-dimensional lattice, then the logical gate is restricted to the div level of the Clifford hierarchy. So for example, if you think 2D toric code, that would be at most Clifford gate. So what we do, the first step we did was that just remove the restriction of geometric locality from this Bravyi-Koenig theorem. So we're saying that if it satisfies a set of conditions, then we can show that this logical gate is in a certain level of the Clifford hierarchy. So once we do that, then we can apply this set of conditions to other code families. And the first code family that we studied is the hypergraph product code. So this code, even though it's not geometrically local, has a pretty nice structure. So it's actually made out of like the tensor product of one chain complex. And so in the case of 2D hypergraph product code, it can be split into like two sectors, and the logical operators has like nice forms for the logical representatives where it's supported on either a single column or a single row. So using, and then similarly for 3D, it will be tensor product of like 3 classical codes. And like toric code is basically the tensor product of 3 classical repetition codes. Then we can like we can understand what the logical representatives look like very visually by like splitting this into 3 sectors, and there's like a canonical logical representatives where they are supported on either like a 2D plane or a single column. And what we can also show is that like this is not just a basis, it's also like a symplectic basis, which is really nice. So there has been some previous work that studies restrictions of logical gates for hypergraph product codes, but this is only for 2D hypergraph product code, and there's a lot of like conditions that they impose for this to hold. So for example, they require that it's like restricted to one sector, and it's only for transversal gate that it is restricted to Clifford group. So in our results, we showed that like for all like dimensions of hypergraph product codes, if your gate is a transversal gate, in the sense that like this U is the product of single physical cubic gates, then U has to be in the Clifford group. And furthermore, we also showed results when U is a constant depth circuit. And so I'm not gonna go through the details of the proof. Yeah, but the idea is for the transversal case is basically we can use the structure of the hypergraph product codes to show that in the end what we get is cannot support any logical qubits, which implies that the region is correctable. And then we can use the conditions in the generalized Bravyi-Koenig theorem to show that it has to be in the Clifford group. So moving on, in the constant depth circuit, it's a bit more complicated, and there's a lot more technical details that go into this. But we managed to show like 3 main results. So first is that if the constant depth circuit maps hyperplanes of a given orientation to possibly different orientations, then then in this case, what we found is that the logical gate is in the level of Clifford hierarchy of L of like L divided by M plus 1, where L is the dimension of the X logical representative and M is the dimension of the Z logical representative. And the second case is that if U is a constant depth circuit that maps hyperplanes to hyperplanes within the same sector, yeah, so this is the result. Yeah, and the main so to give a proof sketch, the main idea is to make use of this dimension reduction. So the basic idea here is that each time when we look at group commutation of the support of ULU dagger with another set of logical representatives, we want to show that the region for this group commutator is given by hyperplanes of lower dimensions. Then if we do this recursively, each round of group commutation will reduce the support of the region to lower dimensional hyperplanes, and finally we get a constant number of lower dimensional hyperplanes. And this constant number, we are able to show that it cannot support any logical qubits, and so it is correctable. Then recursively, we can deduce the we can deduce the level of Clifford hierarchy for like the hypergraph product code. And then the second case is when we consider like U being a constant depth circuit that preserves the orientation for each sector. So what this actually means is that like we on each sector there's the logical representatives take on a certain form and has a certain orientation. So if we do not change the orientation on each of the sector, then we show that like in that case we cannot get logical gates that is beyond the Clifford group. So what this actually implies is that it's very important that we don't have just we do not just have like constant depth circuit that is orientation preserving. Lastly, so the previous two cases are like special cases. One is orientation preserving, and the other one is restricting to the same sector. So more generally, we can for any dimensional hypergraph product codes is made up of like different sectors with different logical qubits on each sector. And we can show that in general, when there are like different sectors and the constant depth circuit can possibly map hyperplanes to different sectors with different orientations, then in that case, we also get a result where the level of Clifford hierarchy is limited to L divided by m plus 1, where L is the dimension of X logical and M is the dimension of a Z logical. Yeah, so one of the main difficulties that we had when working on this is the kind of lack of understanding of like higher levels of Clifford hierarchy. So we know that the first two levels are closed, but the third level is not closed. So because of that, and then on the hypergraph product code, that could be like a lot of logical qubits, we can't restrict our attention to like a few logical qubits in order to show that this code can implement a certain level of Clifford hierarchy. In fact, we have to like study the logical gates that could possibly act non-trivially on all the logical qubits. So this is like a open question. There has not been much done in understanding the Clifford hierarchy beyond the third level. So any further understanding this will definitely help to simplify our understanding of limitations of gates on more general code family. So there's also other questions. So once you have generalized Bravyi-Koenig theorem, so one immediate question is that like beyond hypergraph product codes, is it possible to use the understanding of logical gates to extend these results to other product codes? And then there's also potential generalizations to non-geometrically local code families, such as the Bravyi-Pauling-Terhall bound, which is basically telling you a trade-off between distance logical gates and the number of qubits. Yeah, so thank you for listening.